In this video we're going to consider a particular type of probability distribution called an exponential probability distribution. Now you're somewhat familiar with the idea of probability distributions, so probably the one that we're most familiar with is the idea of the normal distribution, the one that's sort of the bell curve, shaped like a bell curve, and we say we can, things are sort of distributed fairly evenly about the mean on either side. We're going to do lots more on probability distributions, both in methods and specialist, a little bit later in Unit 4. So for now it's just this one, because we're thinking about applications of integration. So let's talk about what the exponential probability distribution looks like. Not surprisingly, it is based on an exponential function. So here we're defining it as a piecewise function, f of x, which for x greater than or equal to 0 has this equation here where lambda is some positive constant. So therefore it's going to be shaped like this. For x greater than or equal to 0, when x is equal to 0, this will be e to the power of 0, which is 1, so we'll just get lambda times 1. So the y-intercept there is going to be lambda, and then it's going to be shaped in an exponential fashion like this, approaching y equals 0 as the asymptote there. Everywhere else, which really just means for negative x, the function is equal to 0. So it's this here. Now that's the form that this takes. So that sort of equation with that graph represents an exponential probability distribution for a random variable x. So one question we might have is, well, what type of random variable x would be modeled by this sort of probability distribution? What kinds of variables would have probabilities that would follow this model? So it turns out that it provides a pretty good model for time between successive occurrences of a random event. Things like customers arriving at a service point, maybe, cars passing a certain point on the road, things which happen fairly randomly can be modeled. Their probabilities can be modeled fairly well by this. What are some other features of this? Well, importantly, we can show that the area under the curve is equal to 1. So that would be represented by the absolute, or the definite integral rather, from 0 to infinity. So this part here, we're saying the area under the curve is equal to 1. And that's a necessary requirement for a probability density function, isn't it? Because the area under the curve represents probability, and probability can't have a total of greater than 1 for any event. Now you could do that fairly easily with a little bit of maths. That wouldn't be hard to show. Turns out that the expected value, or the mean, and the standard deviation of a variable described by this distribution are both 1 over lambda. The mean and the standard deviation are both 1 over lambda. Once again, we could demonstrate that mathematically. And like with any curve that's representing a probability density function, we can find the probability that x lies between a and b by finding the area under the curve between a and b. Alright, so let's now actually look at a specific example where we've got a particular value for lambda and consider how we can calculate some probabilities for that variable. So here we are with a question where x is an exponential random variable with the probability density function as shown here. And we want to find the probability that x is greater than 1, and then the probability that x is less than 2. So here's our value of lambda. In this case is 0.5. So we're going to see 0.5 there and minus 0.5 there, because it's take away lambda x as the exponent. So if we're trying to find the probability that x is greater than 1, we're trying to find the area under the curve from 1 onwards. That's really from 1 to infinity of 0.5 e to the negative 0.5x. If you were doing this on your calculator, then obviously you can't enter infinity there. But really, as long as you enter a large number for that upper bound, and it wouldn't even need to be all that large, probably enter, 10 or something and be fine, but certainly if you entered 100 or 1,000 or something like that, you'd, if you think about how quickly this curve approaches 0 here, you're going to be accurate to a few decimal places, even if you don't put a very large number in there at all. So if we were going to, sort of work this out without a calculator, then we'd be saying, what's the integral of 0.5 e to the negative 0.5x? Well, if we started with e to the negative 0.5x and differentiated that, we'd just end up with pretty much this, except we'd have a negative out the front. So I need to put a negative there to counteract that, and then from 1 to infinity. So you might need to pause for a moment and just convince yourself that that is the integral of this here. But hopefully that wouldn't take you too long. Now, if I'm going to evaluate this at the upper limit at infinity, I can't really sort of enter infinity in there, although I'm really saying what's the value when it's a very large number. So maybe a little bit more sort of accurately, I'd be saying, what's the limit as x approaches infinity of negative, that's what I'm saying, negative e to the negative, let's put the negative in there, negative e to the negative 0.5x, and from that, so take away at the lower bound, it would be negative e to the negative 0.5 when I substitute x equals 1. So what is the value of this? Well, that's really the same as negative 1 over e to the positive 0.5x. Let's just write that up here, so that there is the same as the limit as x approaches infinity of negative 1 over e to the 0.5x. And so what we can hopefully see is as x becomes very, very large, we've got 1 over a very, very large number. Basically, this is approaching 0. So the limit of that there is 0, and then we're adding, what's that, 1 over e to the 0.5. So we could say that it's 1 over e to the 0.5. Now, obviously, then you could, well, if you're using a calculator, you'd probably just do the definite integral anyway, but we could find the approximate value of that using a calculator. Second one here is the probability that x is less than 2. So that's going to be the area from 0 to 2 of 0.5 e to the negative 0.5x dx. So that was negative e to the negative 0.5x from 0 to 2. And so what does that become? Negative e to the negative 1 minus, and this here, e to the power of 0 is 1, isn't it? So it's going to be, take away negative 1, so plus 1. So I might put that term first. And then minus e to the negative 1. I could say that's minus 1 over e. So there it is as an exact value. And again, you could work that out as a decimal. And obviously, because these are probabilities, both of these values here should be between 0 and 1.